Okay. I'll double check. Um, right. Well, because I feel like because I think the 26th was the day I said he doesn't have to come. So I don't think I've marked anyone absent for that day, but I might not have marked you present. So, but yes, I will look at it for sure. Today. More sequences. So, kind of like I was saying last Friday, continue to say, when we talk about sequences, most of the time when we talk about sequences, we are concerned as to whether or not they converge or diverge. Meaning, we're going to be asked to look at their behavior as n, or whatever the subscript is, approaches infinity. So if we have something like, for example, a sub n equal to, oh, thank you so much, appreciate it. Got to turn on the thing, yeah. I didn't even have the, yeah, got to turn it on and also have the thing open and also move it over. There we go. Cool. So if we have a sequence like a sub n equal to -1 to the n times 2n over n squared plus 1. Well, if we start writing out terms, we see that a sub 1 is going to be negative because it's -1 to the first. So we get -2 over 1 plus 1, which is 2. A sub 2 is going to be -1 squared, so that'll be positive. And we'll get 4 over 4 plus 1, which is 5. And so we see that every other term is going to be negative. This is what's called an alternating sequence. We get -6 over 10. A sub 4 is going to be positive 8 over 17, and so on and so on and so on. And when we try to determine whether or not this sequence converges or diverges, we're really just going to look at the non-alternating sequence and kind of figure out what's going on with that, and then talk about what the alternating sequence might do. So here, if we take the limit as n goes to infinity of just the non-alternating part, the 2n over n squared plus 1, we can use the same ideas that we used last class, which is that, so, okay, real talk. We can either do the work or we can use a shortcut. The shortcut being that if the degree on the bottom is larger than the degree on the top, the limit's just going to be 0. So this limit is 0 because the degree on the bottom is strictly greater than the degree on the top. If we don't like that shortcut, we can always show the work being to divide every term by the highest power of n in the denominator. So you have 2n over n squared over n squared, plus 1 over n squared. We simplify that, its limit as n goes to infinity of 2 over n over 1 plus 1 over n squared. And all the things getting divided by n or n to a power end up getting smaller and smaller and smaller, closer and closer to 0. So I end up with 0 over 1 plus 0, and 0 divided by not 0 is 0. But again, I think it's okay to skip this, or just be like, yeah, we know it's gonna be 0 because the bottom's getting bigger faster than the top. Nah. What's that?
Is it ever not true?
It's always true as long as your expression is a rational function, meaning non-negative integer powers of n over non-negative integer powers of n, or polynomial divided by polynomial. So in fact, we'll say that a little bit more. We'll kind of say the general statement in just a second. What I want to point out is that so this sequence, these non-alternating terms are getting closer and closer to 0. So then the alternating sequence is essentially bouncing back and forth between positive and negative numbers that are still getting closer and closer to 0. So if we were to graph things where n was on the x-axis and a sub n was on the y-axis, our a sub 1 is -1, our a sub 2 is 4/5, a sub 3 is -6. And so every time we bounce across, we're getting a little bit closer to 0. Kind of like that. And so the idea here is that, and this also is true, if the limit of the sequence is 0, the limit of the alternating sequence will also be 0. So we can say that the limit as n goes to infinity of -1 to the n times 2n over n squared plus 1 is also equal to 0. And in fact, 0 is the only thing that an alternating sequence can converge to. For a different example, if we said, let's say our sequence is a sub n equal to -1 to the n times 3n plus 1 over 3n plus 2. Well, no, 3n is not what I, fine. That's fine, James. That's totally fine. Not what I meant to do, but it's totally fine. So same idea here as before. If you just look at the non-alternating part, the non-alternating sequence. Wow, can I write the letters? Sure. Which is 3n plus 1 over 3n plus 2. We see that the limit as n goes to infinity of 3n plus 1 over 3n plus 2 is going to be, well, here, since the degree on the top and the degree on the bottom are the same highest power of n, the sequence has a limit that is just the quotient of the leading coefficient. So here it's going to be 3 over 3, which is equal to 1. So the problem here is that if you look at the non-alternating part, that's fine. But if you look at the alternating sequence, well, if n is even, then the terms are getting close to +1. Like if we plug in n equals 2, we get 7 over 9. Sorry, 7 over 8. Apologies. We plug in n equal to 4, we get 12 plus 1, so 13 over 14. We plug in n equal to 6, we get 18 plus 1, 19 over 20, and so on. You can see that, oh yeah, these terms are getting closer and closer to 1. But if n is odd, then the terms are getting close to -1. So if we plug in n equal to, say, 1, we get 4 over 5, and sorry, -4 over 5. If we plug in n equal to 3, we get -10 over 11. Plug in n equal to 5, we get -16 over 17. And we're just getting closer and closer and closer to -1. And the problem with limits is, for limit to exist, the sequence has to be getting close to one and only one specific finite number. That's not happening here. We're bouncing back and forth between 1 and -1. So what that means is an equal to -1 to the n times 3n plus 1 over 3n plus 2 doesn't converge, it diverges. And that's all we can say. But to kind of to say more about the question you asked about the shortcut, yeah, it always kind of works. Let me kind of show you what I mean. So there's 3 cases. So for our shortcut with limits, case one, if the degree on the top is less than the degree on the bottom, then the limit's going to be 0. For example, the limit is n goes to infinity of 3n squared plus 5n plus 1 over 2n to the 5th plus 7n to the 4th plus 3n squared minus 2. For sure, the limit's going to be 0. And you could either just say it is, or if you want to show the work, you would divide each term by n to the 5th power. And then you would see that all the things in the numerator are going to go to 0 because they're all going to be divided by higher powers of n. And the denominator is going to be 2 plus 0 plus 0 plus 0. Case 2, the case that we I feel like see the most, the degree on the top is equal to the degree on the bottom. Then the limit is the quotient of the leading coefficients. Quotient, aka fraction of the leading coefficients. So for example, the limit is n goes to infinity of 5n cubed plus 7n plus 3 over 2n cubed minus 6n squared plus 4. And if you were to take the limit of this, you would end up getting 5 over 2. Because you would divide everything by n cubed. All of the lesser terms would be divided by n squared, divided by n cubed, divided by n, which means they go to 0. And finally, the third case of this situation is when the degree on top is larger than the degree on the bottom. So for example, the limit as n goes to infinity of 5n cubed plus 7n plus 3 over 2n squared minus 6n plus 1. If that's the case where the degree on top is bigger, it means the numerator is getting larger faster, and the limit's either going to be infinity, or it could be, you had something like the limit as n goes to infinity of negative 5n cubed plus 7n plus 3 over 2n squared minus 6n plus 1, negative infinity. For all of these, you could just use the shortcut, or you could divide by, in this case, n to the 5th, in this case, n cubed, in this case, n squared. Let's see what's going to happen. Cool. Yeah.
The exponent is an n.
Yes. So that happens a lot. So then what I say generally is the more general idea of this kind of thing is to divide every term by essentially the thing that's growing the fastest. Let me show you an example. Let's say that we wanted to figure out, let's say our sequence is given by, 2 to the n plus 5 to the n over, what do I want to happen here? Sure, let's say 3 to the n plus 6 to the n. Which is kind of gross. And yeah, we could find some terms. Usually finding the terms is more just to kind of get an idea of what's happening. Like, I think we know how to plug in 1 and get 2 plus 5 over 3 plus 6, which is 7 over 9. And things get gross kind of fast. Plugging into, you get 4 plus 25 over 9 plus 36. And we start to not really care about what the terms look like, because I'm not seeing a real kind of evidence of a pattern by doing this, even if I went a few more terms. So here, if I look at this expression, 2 to the n, 5 to the n, 3 to the n, 6 to the n, well, 6 to the n is the thing that is growing the fastest of all of those, because it's got the largest base. So what I'm going to do is I'm going to divide each of these terms by 6 to the nth power. So I'm going to rewrite this as, actually, I'm going to take the limit first before I start rewriting it. I'm saying I want to look at the limit as n goes to infinity of this expression. And just like in the previous problem, and I should be, no. I'm going to recalibrate a little bit. You might want to divide by the thing that's growing the fastest, or you might want to divide by the thing that's growing the fastest that's in the denominator. So if it was like, if my 6 to the n was on the top, I might divide by the thing that's the biggest number, but we'll kind of look at that in a minute here. So I look at this, I'm going to rewrite this as the limit as n goes to infinity of 2 to the n over 6 to the n plus 5 to the n over 6 to the n over 3 to the n over 6 to the n plus 6 to the n over 6 to the n. We could probably skip this step and simplify. If I skip this step, well, here's the fun fact. 2 to the n divided by 6 to the n is the same as 2 over 6 to the n. Or if you want to, you can reduce that to 1/3 to the n. I have a 5/6 to the n over 3/6 to the n plus 6 to the n over 6 to the n is always going to equal 1, no matter what n is. So now here's the important part. As n gets really, really big, what happens to 2/6 to the n power? Right, exactly. And you can either think of that as just you're multiplying 1/3 by 1/3 by 1/3, or you can even think of it graphically, right? 1/3 to the x. If you think about the graph of this, y equal to 1/3 to the x, or 2/6 to the x, looks like this decreasing exponential function. So you can see that as you go to the right, oh yeah, my values get smaller and smaller and smaller. So what we're going to get here is a 0 plus 0 over 0 plus 1, which is 0. So a lot of these sequences, convergence or divergence, really depends on, is the biggest thing on top or on the bottom? In a similar way, like, so in fact, if we'd asked this question kind of in the reverse way, if I'd said, you know, here's my sequence b sub n equal to, I'm just going to take the reciprocal, 3 to the n plus 6 to the n over 2 to the n plus 5 to the n. I do think it's probably more advantageous to actually divide by the thing that's getting largest, the fastest, that's in the denominator. And let's see why. So if we do it the way I think we should do it, so here's what I would say is the better way. The limit as n goes to infinity of this expression, and I am going to divide everything by 5 to the n. So that's going to be the limit as n goes to infinity. I'm going to do a little bit of simplifying here. Instead of writing 3 to the n over 5 to the n, let's just write 3. Sorry, that's a 3/5 to the n, 6/5 to the n, 2/5 to the n, and 5/5 to the n is just 1 to the n, which is 1. So now here's what's going to happen. The 2/5 to the n goes to 0. The 3/5 to the n goes to 0. But the 6/5 to the n grows infinitely large. So what we end up getting is 0 plus infinity over 1, which is infinity. So this sequence diverges to infinity. I'll point out the reason I think it's better to do it this way is if we do it the other way, so here's the less good way. And in this example, it might not feel quite as less good as other examples. But if we take the limit as n goes to infinity and divide everything by 6 to the n, we're going to get 3 over 6 to the n plus 1 over 2 over 6 to the n plus 5 over 6 to the n. And I don't think it's going to be a problem here. We're going to get 0 plus 1 over 0 plus 0. And we know that a non-zero thing divided by a zero thing goes to infinity. But the problem is that sometimes when you do this, it's unclear if the denominator is slightly negative or slightly positive. Like if this had been a minus 5 to the n instead of a plus 5 to the n, it could have been very much more difficult to figure out that the denominator was doing a positive or negative thing. So I would say it's always better to divide by the highest power in the denominator, because here this can be challenging. It can be challenging to determine the sign. Cool. So a few more things. For example, yeah. I do think it's okay to use that test because it's something I mean, you should ask her. But generally, it's something that we've seen in 16A enough that it's usually assumed to be like, yes, you've seen this and know how to do this. But you might want to check with her. The other thing I noticed you guys were starting to talk about in class was factorials, which you may or may not have seen before. But let's say we had something like a sub n equal to n factorial over 2n factorial. So here we have to be extra careful because the factorials don't just cancel. So if I'm thinking about writing this out, here's how I'm imagining this. I'm thinking of this as, well, n factorial is n times n minus 1 times n minus 2. You just take every lesser integer until you get all the way to 1. Well, it feels kind of silly to write 1 because multiply by 1 doesn't change anything. And then 2n factorial, well, you're starting at 2n and then multiplying by the next smallest integer, which is 2n minus 1. And then going all the way down to, well, I should kind of include these because eventually we're going to get to n plus 1, and then n minus 1, and then n minus 2, and then all the way down to 3 times 2 times 1. And the idea with these factorial kind of expressions is that really what we want to do is cancel something. So here, I can start canceling. So, oh, the n cancels, the n minus 1 cancels, the n minus 2 cancels, all the way down to 3 times 2 times 1. So I can certainly rewrite this. Now, it's a much less nice way of rewriting it, but I could rewrite this as 1 over 2n times 2n minus 1, all the way down to n plus 1. Now, as far as clarity of writing, I would always choose to write this. But if I'm being asked to determine convergence or divergence, so if I ask the question, does a sub n converge or diverge? Well, then I'm going to look at this way of rewriting it, because I'm going to take the limit as n goes to infinity of a sub n. And it's much easier to see that if we write it in this way, as 1 over 2n times 2n minus 1, all the way down to n plus 1, well, clearly the denominator is getting very large and the numerator is just 1, so we're getting 0. And it's useful to be able to kind of manipulate these factorial expressions because they are going to keep showing up. Yeah, let's look at one more example of this. Then we'll talk about one more thing. And I think we can start on this series. Oh, actually, no, there's one of the maybe 4 series. So 2 more expressions I think are kind of interesting. Let's say we want to find, let's say our sequence is a sub n equal to n factorial over 4 to the nth power. And I want to know, does this converge or diverge? So here's some bad news. We cannot use L'Hopital's rule if there's a factorial involved, because we don't know, it's not really possible to differentiate the n factorial function. So L'Hopital's rule is off the table. And this one's kind of tricky. So the way we're actually going to deal with this one is by looking at things term by term for a second. So we're going to write some terms. A sub 1 is 1 factorial over 4 to the 1. By the way, 1 factorial is just 1. Also, interestingly, 0 factorial is also defined to be equal to 1. It's kind of like how 5 to the 0 is equal to the 1. It's one of these, it's kind of a consequence of laws in mathematics that we need to be true. So yes, it is true that 0 factorial is equal. Continuing on here, a sub 2 is 2 factorial over 4 squared, which looks like it's smaller than the previous term. It's 2/4 times 1/4, which is equal to 2/4 times the previous term, a1. A sub 3 is 3 factorial over 4 cubed, which is 3/4 times 2/4 times 1/4. But that's just your second term. So this is 3/4 of the second term. So still smaller than the previous term. So far it looks like things are decreasing. started with 1/4, and then I got 1/8, and then I got something smaller than that. But now things are going to change. A sub 4 is going to be 4 factorial over 4 to the 4th, which is really 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. And that term there, in parentheses, is your A sub 3, and you're multiplying it by 4 over 4, so it's the same. So it didn't get smaller. And then the next term is actually going to get larger. So A sub 5 is going to be 5 factorial over 4 to the 5th, which is 5/4 times 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4, which is bigger than the previous term. And it looks like every subsequent term is going to get larger, right? It looks like A sub 6 is going to be 6/5 times A sub 5. A sub 7 is going to be larger than A sub 6. 6/5 is the wrong fraction. I should have said 6/4, not 6/5. Similarly, that should have been 7/4. That's why it's good to keep writing out the pattern until you're absolutely sure of it. So we can confidently say here that the limit as n goes to infinity of n factorial over 4 to the n is going to be infinity. The terms keep growing and growing and growing. But really, this is kind of just done by inspection. Right? We looked at enough terms to convince ourselves, yeah, that every next term is going to be larger than the previous one. And so it's going to just keep growing and growing and growing. Something to take away from this, in fact, something that I think is worth noting in general is kind of the answer to the question, which functions grow fastest or slowest? Well, the fastest is n factorial. So over here on the fast end of things, it's n factorial. And then somewhat less fast than that is exponential functions like 3 to the n or 5 to the n, or essentially anything raised an exponential like that. B to the n would be a more general way of saying that. And then slightly less fast than that are polynomials like n cubed or n to the 7th power. And then even less fast. So now we're getting kind of on moving towards the slow side of things. You have just n to the 1st. I might not have given myself enough room on the slow side here. And then even slower than that, we have like the nth root. So like n to the 1/3 or the 5th root of n, that kind of deal. And even slower than that, you would have. So really what I'm doing in this opposite direction here is I'm kind of finding the inverse functions. So the inverse of n to the 3rd is n to the 1/3. The inverse of 3 to the n is like log base 3 or the natural log. So over here we have like natural log of n or log base 3 of n. And that's kind of the general list of which things grow fastest, grow the fastest or the slowest. Logarithms are the slowest, roots are the next slowest, linear things are kind of right in the middle, powers of n are the next fastest, exponential functions are pretty fast, but then even faster than exponentials are n factorial. And then if you really want to get fancy, over here even further to the right is n to the nth power. That's going to grow even faster. So when you're kind of thinking about what you think might happen. So for example, if I said, what's the limit as n goes to infinity over, I don't know, n cubed over 3 to the n? Well, because I know that the exponential things grow faster than the polynomial things, I'm pretty sure that this fraction is going to get smaller and smaller and smaller because the denominator is the thing that grows faster. So now, what about something like this? Well, this is what's called an indeterminate form. We might have seen this back in, I don't know, a quarter or two ago. We might not have. But if you think about taking the limit as n goes to infinity of 1 plus 1 over n to the n. Now, what I would say is this is what's called a 1 to the infinity type. What I really want to say is the base isn't 1. It's getting really, really close to 1. And then exponent isn't infinity, it's just getting really, really large. So what you have is a number that's not quite 1 getting multiplied by itself a lot of times. And what's going to happen there is that being multiplied by itself so many times is going to kind of overcome the fact that it's so close to 1. And you're not just going to get 1. You're not going to get 1 times so much times. You're going to get something just a tiny bit bigger. And so what's going to happen is this limit, while you do it the long way, the limit as n goes to infinity of 1 plus 1 over n to the n, we can write as the limit as n goes to infinity of e to the natural log of 1 plus 1 over n to the n. We can bring that n down in front, but then instead of bringing it down in front, we're going to write this as the limit as n goes to infinity. I'll write it that way first. E to the n times natural log of 1 plus 1 over n. But then what I really want to do is write it as the limit as n goes to infinity of e to the natural log of 1 plus 1 over n over 1 over n. And the reason I want to do that is because then I can use L'Hopital's rule, because that exponent there, that fraction, the top of that fraction is natural log of 1 plus 1 over n. As n goes to infinity, 1 over n goes to 0, 1 plus 0 is 1, and the natural log of 1 is 0. And the bottom is also going to 0. So we have a 0 over 0 type, which means we're allowed to use L'Hopital's rule. And so then what we can say is that this is going to equal the limit as n goes to infinity of e to the, we take the derivative of the top, it's 1 over 1 plus 1 over n times the derivative of the inside, which is negative 1 over n squared, over the derivative of 1 over n, which is also negative 1 over n squared. Those cancel, and we're left with the limit as n goes to infinity of e to the 1 over 1 plus 1 over n. And then as n goes to infinity, 1 over n goes to 0, and you're left with e to the 1 over 1, which is just e. And the reason I bring this up is because it comes up relatively often. So usually people are fine with students kind of just being like, yeah, I know that's going to be that, instead of showing this work every time. But then the more kind of general formula is that, I can move this paper here. Maybe someday. Maybe not. Maybe you can see the picture. So it's commonly accepted that the limit as n goes to infinity of 1 plus x over n to the nth power is equal to e to the x. And this comes up moderately frequently. So for example, just putting this one into practice here, if someone said my sequence a sub n was, sure, n over n plus 3, the nth power, I'm going to work to make this look like that, which is a little challenging. So I really want to flip this over. N over n plus 3 is not helpful to me. I'm going to rewrite this as 1 over n plus 3 over n to the n, which is totally allowed, right? I'm really just saying it's n plus 3 over n to the negative n and then bringing it back to the top. But then the reason I want the fraction to have like the more than one term on the top is so I can divide each thing by that n. So I'm going to write this as 1 over 1 plus 3 over n to the n. And then I can say, great. I should have started with the limit. The limit as n goes to infinity of n over n plus 3 to the n, the thing I started with, is equal to the limit as n goes to infinity of this. but the limit as n goes to infinity of 1 plus something over n to the nth power is equal to e to that something. So this is going to equal 1 over, the limit of this is going to be e to the third. So the limit of this sequence is e to the negative third. Feels a little bit weird, but it's not that weird. The other thing we do with sequences before we start talking about series is sometimes we're asked to find the formula for sequence. And this becomes somewhat important later on when we're talking about sequences, being able to identify like what the pattern actually looks like. So let's start with an easy one. We're going to find the formula for the sequence A sub n. So here's my first example. Let's say it's 5, 9, 13, 17, 21. So when I look at the sequence and I'm trying to identify the pattern, there are 3 things I look for. One, the first thing I look for is, do the terms just increase by the same amount each time? In this case, yes. In this case, we're increasing by how much each time? Right. So if you're increasing by the same amount each time, what we're going to have then is a 4 times n. And the way I kind of think about this is, well, in fact, I'm going to write it this way. This first term is when a sub 1, that's a sub 2, that's a sub 3, that's a sub 4, that's a sub 5. The subscript n is increasing by 1 every time. That's just how it works, right? A sub 1, a sub 2, a sub 3, a sub 4, right? So if you want your sequence values to increase by 4 every time, well, we're going to take that and then multiply it by 4. So we're going to say that a sub n is equal to 4 times n. And then we're going to adjust. If I left it like that, it'd be wrong, because my a sub 1 would be 4, my a sub 2 would be 8, my a sub 3 would be 12, and so on. I'm off by 1, so I'm going to add 1. And then I can check if you be like, oh yeah, a sub 1 is 4 plus 1 is 5, a sub 2 is 8 plus 1 is 9, and so on and so on and so on. So that's what I usually look for first, is are things just increasing by the same amount of time? And it applies for fractions as well. If my sequence were to start off as, say, 5/8, 7/11, 9/14, 11/17, 13 over 20, I'm usually looking at the numerator and the denominator separately. So looking at the numerator, I see 5, 7, 9, 11, 13. Oh, we're increasing by 2 each time. So I can think of my a sub n formula as being 2 times n plus or minus something. And then for the denominator, looks like I'm increasing by 3 each time. I didn't finish that off yet. There's something that's going to go in there. For the denominator, I'm increasing by 3 each time. Plus 3, plus 3, plus 3, plus 3. So I'm going to get a 3n. And then what I'm really going to do is I'm going to say, well, I know I'm starting at n equals 1. If I plug in n equals 1 to the numerator, I get 2 times 1, which is 2, but I wanted to get 5, so I'm going to add on 3. And then the rest of it works out, because I'm just increasing by 2 every time. I plug in n equals 2, I get 4 plus 2, which is 7. Plug in n equals 3, I get 6 plus 2, which is 9. For the denominator, I do the same thing. If I plug in 1, I get 3 times 1, but I want to get 8, so I add on the difference, which is 5. And that works out just fine. So if things are increasing by the same amount each term, it's relatively easy to find the pattern for it. It's a little bit more difficult if we have something else going on. And again, if you need to go, Heather, it's totally fine. You're always welcome to just like pick up and leave. I know you're not leaving because you don't like me. I know you're leaving because you need to go. I'm going to keep talking to no one though, because I'm going to say something. So if our pattern, on the other hand, is something like this, 5, 10, 20, 40, 80, now the difference between terms is not the same each time. And the difference here is 5, the difference is 10, the difference is 20, the difference is 40. But interestingly, the difference is kind of the same pattern that we started with, right? We still have 5, 10, 20, 40. If we do it again, we're going to get 5, 10, 20, and so on. So when you see this kind of repeating difference of differences, it speaks to a different kind of thing. Instead of having like an arithmetic sequence like we had in the previous examples, arithmetic is just where the terms increase by the same amount each time. Here we have something that's more geometric. We're multiplying by the same amount each time, right? If you think about it here, from 5 to 10, we are multiplying by 2. From 10 to 20, we are multiplying by 2, multiplying by 2, multiplying by 2. This is what an example of what's called a geometric sequence. And so typically, whatever you're multiplying each term by, instead of having like 2 times n, we're going to have 2 to the nth power. So we're going to have something like 2 to the n, but then we need to multiply by the right thing. So there's a couple ways to approach this. I'm thinking of my a sub 1 equals 5, my a sub 2 equals 5 times 2, my a sub 3 equals 5 times 4, my a sub 4 is 5 times 8. Notice I'm writing this powers of 2. My a sub 5 is 5 times 16, which is 5 times 2 to the 4th. I could try to do the same thing I did before and say, well, I know I'm going to have a 2 to the n, and then I need to basically make my first term work. So I plug in n equals 1, I would get 2, but I want to get 5, so I multiply by 5 halves. And that would totally work. If this is my a sub, my a sub n, I'm getting a sub 1 is 5 over 2 times 2. A sub 2 is 5 over 2 times 2 squared. A sub 3 is 5 over 2 times 2 cubed. And they all match up, right? 5 over 2 times 2 cubed is the same as 5 times 2 squared. Or we kind of look at this and say, well, here I have a 2 to the 0. 1 is 1 bigger than 0. 2 is 1 bigger than 1. 1 bigger than that. 1 bigger than that. 1 bigger than that. So we could just say that our formula for our nth term is 5 times 2 to the n minus 1. If that's n, that's n minus 1. That's n, that's n minus 1, n minus 1. So every time you're trying to look to kind of see like what's increasing by 1 every time and how does that compare to what my n is. There's one other thing I want to mention. Kind of. Yeah, we'll see about that later. The other thing, so I guess there really is one other, oh, I know what it is. Yeah. So if your difference, like in the previous examples, is constant, so like difference was 4 every time, so we got a 4n. Difference on top was 2 every time, we got a 2n. Difference on the bottom was 3 every time, we got a 3n. Here, the difference kind of repeated every time you did. So if you kept doing the difference, you would still get the same thing every time. But there's one other kind of thing that can happen. Well, this is a lot of things. But the other kind of thing I want to mention that can happen is if you had something like this, like if your a sub n was equal to, let's make it interesting. Let's say 7, 12, 19, 28, 39. So if this is the case, I'm gonna give you one more term even. 42. So if you start looking at the differences, it doesn't seem like, well, there's maybe a pattern. I see a 5, a 7, a 9, an 11, a 13. Oh, look, those are differing by odd numbers. If you look at the difference of the difference, oh, you get constants. Now, the difference of a difference is a constant. It's kind of like the second derivative being constant. In fact, if you go back to the example from the first example, right? If you think about the difference being 4 every time, it's kind of like the derivative with respect to x of our function being 4. And so then the antiderivative of 4 is 4x plus c. So our a sub n is 4n plus a constant, and that constant happens to need to be 1. While if the second derivative is constant, so if our f double prime of x is equal to 2, then the first antiderivative is just the derivative, which is 2x. Maybe there's a constant. I don't think there actually is here, whatever. And then your antiderivative of that, the antiderivative of 2x is x squared. And there might be some other constants and stuff here. I'm not too worried about the constants. It's kind of just a general analogy here. So x squared actually is the right idea. So, but how do I get there? Because it's a little challenging. Well, let's see here. I know that if I just said a sub n was n squared, then my a sub 1 would be 1. Or let's just write the pattern. I would get something like 1, 4, 9, 16, 25, 36, 49, et cetera, et cetera, et cetera. That should have been a 52. I am so sorry. You guys are like, the difference between 39 and 42 is not 13. Sorry about that. That should have been a 52. Apologize. And so on. If I look at the corresponding differences here, there's a difference of 5, there's a difference of 7, there's a difference of 9, 11, 13. So it kind of looks like I shouldn't really be starting with a sub n equal to 1. So I could say that my pattern is a sub n equal to n squared, and then I need looks like a +3 to get all those. And then I'm starting at n greater than or equal to 2. But usually we don't like that. So to fix that, well, if I want to start at n equal to 1 instead, here's how I do it. I say n of the a sub n should equal, I'm still going to go with n squared plus 3 for a second, but then essentially where n is greater than or equal to 2, I want to start at a different letter. So I'm going to say, well, I want to start at m equal to 1 instead of n equal to 2. So that means m should equal, if n starts at 2 and m starts at 1, then m is 1 less than n. I should say that m is equal to n minus 1, or that m plus 1 is equal to n. So I'm going to replace my n with m plus 1. So my a sub m is equal to m plus 1 squared plus 3. This one here starts at n equal to 2, which is totally valid, because we usually like to start at n equals 1. This one here starts at m equal to 1, but they're still the same, right? If m equals 1, I get 2 squared plus 3. If n equals 2, I get 2 squared plus 3. If m equals 5, I get 6 squared plus 3. If n equals 6, I get 6 squared plus 3. We're getting all the same terms. And if you don't like using an m, you can then change it back and say a sub n is equal to n plus 1 squared plus 3. But now we're starting at n equal to 1 instead of equal to 2. All right, that's all I've got for today. We will talk about series on Wednesday, which is where you add up all the terms of your sequence.